Today we are going to discuss the preparation methods of haloarenes. Here first method is given from hydrocarbon by electrophilic substitution reaction. So let's read from the book. Aryl chloride and bromide can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid catalyst like iron or iron 3 chloride. And here reaction is given in which toluene when react with X2 in the presence of Fe in dark, it produces ortho halotoluene and para halotoluene. So let's try to understand how this reaction take place. So first of all draw the toluene. Toluene means CH3 group is bonded to benzene ring, then it is called as toluene. So this is benzene and when it is bonded to CH3, it is called as toluene. So toluene is the common name. When it react with X2, X2 can be Cl2 or it can be Br2. In the presence of Lewis acid, here Lewis acid is Fe or it can be Fe3 chloride. In dark, it produces ortho halotoluene and para halotoluene. So this is toluene. When halogen attached to ortho position, it is called as ortho halotoluene. This is ortho halotoluene. And another product which is formed is para derivative of toluene. So this is CH3 and para position is the diagonal position. So when X get attached to the diagonal position, it is called as para halotoluene. As benzene undergo electrophilic substitution reaction. For the electrophilic substitution reaction, electrophile is required. An electrophile is generated by the reaction of Lewis acid. So when X2 react with Lewis acid, here Lewis acid can be FeCl3, Fe3 chloride. This is FeCl3. When it react with FeCl3, it results in the formation of FeCl4 negative and X positive ion. This X positive is the electrophile. Because it is electron deficient, this is electron deficient. As it is electron deficient, it is electron loving. And electron loving species is electrophile. So here electrophile is X positive ion. Now let's see at which position it get attached to toluene. So this is toluene, benzene ring and CH3 group is bonded to benzene is called toluene. This CH3 group donates electron density to benzene ring by plus I effect. As it donates electron density to benzene ring, it donates electron density at ortho as well as para position. That's why it is an activating group. This is activating group. As it is activating group, it directs the coming electrophile at ortho and para position. So that's why it is called as ortho-para directing group. Means it directs the coming electrophile to get attached either to ortho position which is adjacent position or at para position which is a diagonal position. So let's take one example. So this is toluene in which CH3 group is bonded to benzene. When it reacts with Cl2 in presence of FeCl3 in dark, Cl positive electrophile will generate and which will either get attached to ortho position or it will get attached to para position. So when it get attached to ortho position, it results in the formation of ortho derivative. So this is toluene and here Cl get attached to ortho position. So it results in the formation of orthochlorotoluene. And if it get attached to para position, it results in the formation of parachlorotoluene. So this is toluene, and Cl get attached to para position. So this is named as parachlorotoluene. And byproduct will be formed, which is HCl. HCl is the byproduct. Now let's read from the book. The ortho and para isomers can be easily separated due to large difference in their melting point. So let's see how their melting point is different from each other. Let's draw the structure of ortho and para derivative. So this is benzene, and here is CH3 group. Again I am going to draw the same structure, toluene, this is CH3. And this is para derivative. So here Cl is attached at para position, and this is ortho derivative where Cl is attached at ortho position. Now let's compare them. As CH3 is electron donating group, it donates electron density to benzene ring. That's why it develops positive charge. And as Cl is the electron withdrawing group, being more electronegative than carbon, it withdraws electron density from benzene ring, and as a result of it, it develops negative charge. So that's why the molecule is polar in nature. Same here also. Here CH3 donate electron density through plus I effect and develop positive charge, and Cl withdraw electron density from benzene ring, so it develops negative charge. So that's why both the molecules are polar molecule. But in case of para derivative, the molecule is symmetrical. But ortho derivative is asymmetrical. Because para derivative is symmetrical, so close packing of this molecule is possible. So it can be packed closely. But it cannot be packed closely. As it is packed closely, the van der Waals force of attraction between the molecule is more. Van der Waals force of attraction will be more. As there is more van der Waals force of attraction, the melting point will be higher. But in case of ortho derivative, as the molecule is asymmetrical, close packing of the molecule is not possible. So it will have less van der Waals force of attraction, and that's why its melting point will be lower. Now let's read from the book. The ortho and para isomer can be easily separated due to large difference in their melting point. The reaction with iodine are reversible in nature and require the presence of an oxidizing agent like HNO3 or HiO4 to oxidize the Hi formed during the iodination. So let's try to understand it, why iodination is reversible in nature. First of all, draw the structure of toluene. So this is toluene, in which CH3 group is bonded to benzene. When it reacts with I2, in presence of Lewis acid, Fe, it results in the formation of ortho and para isomers. So this is toluene, and here this is ortho derivative, and here this is another structure. So this is toluene, and this is para isomer, in which iodine is get attached to the para position. And the byproduct Hi is formed. This Hi is responsible for the reversal of this reaction. This Hi is a strong reducing agent. So this Hi is a strong reducing agent. So let's revise what is reduction. Reduction is the addition of hydrogen or the removal of electronegative element. So reduction is addition of hydrogen or removal of electronegative element. Removal of electronegative element like oxygen or any electronegative element. Here electronegative element is iodine. So because of the formation of Hi and as it is a strong reducing agent, it removes iodine from the formed product. So when it removes iodine from the formed product and add hydrogen in place of iodine, it results in the formation of the reactant again. So that's why because of the formation of Hi, this reaction is reversible in nature. If somehow we are able to destroy the formed Hi, this reaction can be performed in the one direction, that is forward direction only. Hi can be destroyed when it reacts with HNO3, which is a strong oxidizing agent. So here when it reacts with HNO3, HNO3 is an oxidizing agent. It is oxidizing agent. So it oxidizes Hi. When it oxidizes Hi, I2 is formed. So this I2 is the reactant and which again take part in the reaction and favors the forward reaction. That's how addition of HNO3 or HiO4 favors the forward reaction, while the formation of Hi is responsible for the reversal of the reaction. Now let's read from the book. Fluorocompounds are not prepared by this method due to high reactivity of fluorine. Fluorine is more reactive than other halogen. That's why fluorocompounds cannot be prepared by this method. Now come to the next method. The preparation of haloarene from amine by Sandmeyer reaction. When a primary aromatic amine dissolves or suspended in cold aqueous mineral acid is treated with sodium nitrite, a diazonium salt is formed. Mixing the solution of freshly prepared diazonium salt with cuprous chloride or cuprous bromide result in the replacement of diazonium group by Cl or Br. Here reaction is given. This is aniline. When it reacts with NaNO2 and HX at 273 to 278 Kelvin temperature, it results in the formation of benzene diazonium halide. When this benzene diazonium halide reacts with cuprous halide Cu2X2, it results in the formation of aryl halide and byproduct N2 is formed. So let's try to understand how this reaction takes place. So here this is benzene where alternate single and double bonds are there, and here NH2 group is there, which is amine group. When amine group is attached to benzene ring, it is called as aniline. This is aniline. When it reacts with NaNO2, sodium nitrite, and any mineral acid is the haloacids. So here HX. When it reacts, it results in the formation of diazonium salt. So this is benzene to which N2 group is attached. Here nitrogen, there are two nitrogen, and as this nitrogen forms 4 bonds, it develops positive charge. To neutralize this positive charge, X negative ions are present. This group is called as diazo group. Di means 2, azo means nitrogen. So this is diazonium halide. When this diazonium halide react with cuprous salt, when it react with Cu2X2, X negative is a nucleophile. It replaces N2 group from diazonium halide. So when it replaces N2 group, it results in the formation of halobenzene. So this is benzene, and as X minus replaces N2 group, it takes the place of N2 and result in the formation of halobenzene. And N2 will be released in the form of N2 gas. So that's how Sandmeyer reaction takes place. Now let's take another example. Here there is aniline, benzene, to which N2 group is attached. When it reacts with NaNO2 and HCl, it results in the formation of diazonium chloride. So here this is N, triple bond N. It carries positive charge, and to neutralize this positive charge, Cl negative ions are there. When it reacts with Cu2Cl2, here Cl negative nucleophile is formed. So it is nucleophile. It replaces N2 from diazonium. So as a result of it, chlorobenzene is formed. So this is benzene, and here Cl group will get attached to benzene ring, and N2 is released in the form of N2 gas. Similarly, you can prepare bromobenzene by using HBr in place of HCl and Cu2Br2 in place of Cu2Cl2. So in that case, you will prepare bromobenzene. Now let's read from the book. Replacement of diazonium group by iodine does not require the presence of cuprous halide, and it is done simply by shaking diazonium salt with potassium iodide. Means for the formation of iodobenzene, it doesn't require Cu2I2. You can simply shake the diazonium halide with Ki, and you will get iodobenzene. Now let's solve this question. Write the product of the following reactions. Here there is first reaction. First of all, identify the functional group. So here functional group is alkene and the reagent is HBr. To get the product of this reaction, you have to follow Markovnikov rule. According to Markovnikov rule, negative part of the reagent goes to the carbon that is bonded to less number of hydrogen. So this is the Markovnikov rule. So first of all, identify the negative part of the reagent. Here reagent is HBr. So H is positive and Br is negative. So negative part of the reagent is Br negative. Now check which carbon is bonded to less number of hydrogen. So let's draw the structure first. Here there is benzene ring to which alternate single and double bonds are there, and this is alkene to which hydrogen, and here also hydrogen is bonded, and here also hydrogen is bonded. So double bond is present between these two carbons, and among them which one is bonded to less number of hydrogen? So this carbon is bonded to less number of. One of the bond of double bond will break, and as a result of it, your negative part of the reagent, which is the Br negative ion, will get attached to the carbon which is bonded to less number of hydrogen. So Br will get attached to this carbon. So here Br will get attached and H will get attached to the another carbon. So this will be the product of your reaction. Now come to the second question. Here there is again alkene is given and you have to do the reaction with HCl. In HCl, Cl is the negative part of the reagent and H is the positive part of the reagent. So Cl will get attached to the carbon, sp2 hybridized carbon, which is bonded to less number of hydrogen. So Cl will go to the second carbon and H will get attached to the first carbon. So let's write down the product of this reaction. This was the first reaction and now we are going to do second reaction. So the product of second reaction will be CH3 single bond CH2 single bond CH single bond CH2. So here Cl will get attached to the second carbon and H will get attached to the first carbon. Now come to the third reaction. In third reaction again double bond is there and you have to do the reaction with HBr. But in presence of peroxide, when the addition of HBr takes place, so when the addition of HBr takes place in presence of peroxide, this is the special case. So addition of HBr in presence of peroxide, you have to follow anti-Markovnikov rule. So anti-MK rule, you have to follow anti-MK rule. Means now negative part will go to the carbon which is bonded to more number of hydrogen. So according to anti-Markovnikov rule, now negative part will go to the carbon that is bonded to more number of. So this is the anti-Markovnikov rule. So now identify which carbon is bonded to more number of hydrogens. So here this carbon is bonded to more number of hydrogen and Br is the negative part, H is the positive part of the reagent. So now negative part will go to the first carbon and positive part will go to the second carbon. So let's write down the product of this reaction. So the product of this reaction will be benzene. It is bonded to CH2 single bond CH single bond CH2. So according to anti-Markovnikov rule, H will go to the second carbon and Br will get attached to first carbon. Now let's solve the Intext question. Now let's solve this question. Why is sulphuric acid not used during the reaction of alcohol with Ki? So let's see what will happen if we use sulphuric acid with Ki. Sulphuric acid is a strong oxidizing agent. So it oxidizes Ki into Hi and further oxidizes it into I2. This I2 cannot produce nucleophile which can substitute OH negative ion from the alcohol. So here we can write this I2 cannot produce nucleophile that can substitute hydroxide from alcohol. So that's why it doesn't support the reaction of alcohol with Ki. So this was 6.2. Now come to the next question. Write the structure of different dihalogen derivative of propane. So here you have to form dihalogen derivative. So this is the question number 6.3 and we have to write the structure of different dihalogen derivative of propane. So first of all draw the structure of propane. So propane contains 3 carbon. There are 3 carbon. Now balance the hydrogen. So here CH3, H2 and this is H3. So this is propane. Now you have to substitute any two hydrogens with halogen. So let's take halogen, chlorine. Now let's draw the structure of dihalogen derivative. Let's try first. This is C, C and C. So first of all we can attach two chlorine at the terminal carbon. So here there are two chlorines can be attached to the terminal carbon. Now balance hydrogen. So here you can write H. This is H2 and here CH. So this is first structure. Now draw the second structure. Here we can draw C, C and C. Now this time we can attach both the chlorine to the middle carbon. So here we can attach both the chlorines to the middle carbon. So here Cl and Cl. Now balance the hydrogens. So at the terminal position H3 and here also H3. Now draw the third structure. So here we can draw C, single bond C, single bond C. Now we can draw vicinal dihalide. So this time we can attach chlorine to the adjacent carbon. So here Cl and this is also Cl. Now balance the hydrogens. So here CH3, here CH and here CH2. Now one more thing we can do, we can attach chlorine to the terminal position only. So here C, C and C. So this time we can attach one chlorine at this carbon and one chlorine at this carbon. So here is Cl and Cl. Now balance the hydrogens. So we can write CH2, here H2 and here H2. So that's how we can draw these different structures of dihalogen derivative of propane. Now solve the next question. Among the isomeric alkane of molecular formula C5H12, identify the one that on photochemical chlorination yields a single monochloride. Here alkane is given pentane. Pentane, it is C5H12. In first question we have to draw the structure of single monochloride that can be formed during the chlorination of pentane. So here you have to draw the structure of pentane in such a way that all the hydrogen should be equivalent to each other. Means when you replace any of the hydrogen you will get the same product. So here we can draw the skeletal structure of pentane in this way. So if we draw the structure of pentane like this, now balance the hydrogen. Here CH3, here also H3, here also H3 and here also H3. So if you see, all the hydrogens are equivalent. They all are primary hydrogen. So if you replace any of the hydrogen, you will get the same product. So by the chlorination of this pentane, you will get the same structure every time. So this pentane will lead to the only one single product of monochlorination. So here you can write CH3, C, CH2, CH3, CH3 and chlorine will get attached to one of the carbon. So here you can draw chlorine. This will be the only product formed by the chlorination of this pentane. So this is first question. Now try to solve the second one. Here you have to draw the structure of 3 isomeric monochloride. So this time we have to draw the structure in such a way that leads to the formation of 3 isomeric monochloride of pentane. So let's try to draw the structure. Here CH3, CH2, CH2, CH2 and this is CH. Now let's see how many type of hydrogens are there. So there is these terminal hydrogens, primary hydrogens are there and secondary hydrogens are there. But when you replace these two hydrogens, they will lead to the formation of same kind of product. And the middle one will lead to the formation of third kind of isomer. So let's try to draw the structure of monochlorides. If we replace the terminal hydrogen, you will get product Cl, CH2, 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 CH2 and CH3. When you write the IUPAC name, you will get 1-chloropentane. Even if you replace this terminal hydrogen, then also you will get 1-chloropentane. Now if you replace this blue hydrogen, the secondary hydrogen, you will get the product CH3, CH, single bond CH2, here CH2, this is CH3. So this time we have replaced secondary hydrogen. And the IUPAC name of this molecule will be 2-chloropentane. If you replace this hydrogen also, you will get the same product 2-chloropentane. But if we replace the middle hydrogen, you will get the product CH3, CH2, CH, CH2 and CH3. So here if you replace this hydrogen, you will get 3-chloropentane. None other monochloro derivative can be obtained by the reaction of this pentane. This is N-pentane. Now solve the third question. Here you have to draw the structure of 4 isomeric monochlorides of the same pentane molecule. So this time we can draw the structure in such a way that leads to the formation of 4 isomeric monochlorides. Let's draw the structure of pentane in which 4 kind of hydrogens are there that leads to the formation of 4 different monochlorides. So this is CH3, single bond C, single bond C and single bond C. We can make one of the branch of another CH3 here, CH3 and there is hydrogen. When you balance it, you will get CH2, single bond CH. Now let's find out how many types of hydrogen are. So this CH3 and this CH3 are equivalent to each other. When you replace any of the hydrogen, you will get the same product. And if we replace this CH3, it will lead to the formation of another kind of product. And here if we replace this CH2, it is secondary hydrogen. So it will lead to the formation of third product. And if we replace this hydrogen, it results in the formation of fourth kind of isomer. So let's draw the structure of each isomer. So here Cl, if I replace this yellow one, Cl, CH2, single bond CH, here's branch of CH3, this is CH2 and this is CH3. Now name this molecule. When you number the chain from left direction, you will get 1, 2, 3 and 4. This is methyl substituent. So the name of this compound will be 1-chloro-2-methyl-butane. Now draw the another structure. So here we can replace the blue hydrogen. So here you will get CH3 single bond CH, single bond CH3, here CH2, this is CH2 and this time Cl will get attached to the terminal position. So now again number the chain. So this time we are going to number it from the right direction 1, 2, 3, 4. So the name of this molecule will be 1-chloro-3-methyl-butane. Now let's replace the green hydrogen. So in that case you will get CH3 CH single bond CH3. This is CH single bond Cl and here CH3. Now number the chain from right direction because we have to give lowest possible number to the functional group which is chlorine. So the name of this molecule will be 2-chloro 3-methyl butane. Now if we replace the purple one, you will get CH3 C CH3 CH2 CH3 and this time we have replaced this hydrogen. So now this time you have to number the chain from the left direction. So this is 1, 2, 3 and 4. So the name of this compound will be 2-chloro 2-methyl butane. So that's how you will get 4 isomeric monochlorides of pentane. Now let's solve the next question. Here in the first reaction, this alcohol when react with thionyl chloride, Cl will replace OH and you will get the product. This is cyclohexane. In place of OH you have to write Cl and byproduct will be SO2 and HCl. This is the best method for the preparation of alkyl halide from alcohol that we have studied. In this second question, there is benzene ring in which CH2 CH3 group, ethyl group is there and NO2 group is attached. When it reacts with Br2 in presence of UV light means free radical reaction. So benzene do not take place in the free radical reaction mechanism. So this time your target molecule will be the alkyl group which is attached to the benzene ring. In this case you will get the product. There is benzene ring which do not take part in the free radical reaction mechanism. This is NO2 group. It will also do not take part in this reaction. So target functional group or target molecule will be this CH2 CH3 group. So here there are two types of hydrogen. One is the primary hydrogen and another one is the secondary hydrogen. So this hydrogen is primary hydrogen and this hydrogen is secondary hydrogen. So whenever reaction takes place, secondary hydrogen will be replaced by the halogen. So as a result of it, when it reacts with Br2 in presence of H nu, you will get the product. This is benzene ring. Here NO2 group is there. And this is CH single bond CH3 and bromine will get attached to the second carbon. So this is the monohalo product formed by this reaction. Now come to the third reaction. In this reaction, when this alcohol react with HCl, so there are two OH. So which will take part in the reaction? Now let's draw the structure first. Then we will identify the type of OH group present in the molecule. So this is benzene ring and here CH2 OH is there and this OH is there. The OH which is bonded to benzene ring. This OH is phenolic alcohol. This is phenolic group. This alcohol do not take part in the reaction. While the another alcohol which is bonded to CH2 group, it will take part in the reaction. So when HCl react with this molecule, Cl will replace this Cl will replace this OH, but not this OH. So now let's draw the structure of our product. Here this is benzene ring in which alternate single and double bonds are there and there is CH2 and this OH will get replaced with Cl. So Cl will get attached to this CH2 and here is OH, which is phenolic. And this OH cannot take part in this nucleophilic substitution reaction. This is a kind of nucleophilic substitution reaction in which Cl negative replaces OH negative. Now come to the fourth reaction. Here there is alkene, and when it reacts with HI, you have to find out the product of this reaction. So whenever there is reaction of alkene, you have to follow the Markovnikov rule. So first of all, draw the structure of alkene. So this is cyclohexane and there is double bond, so it becomes cyclohexene, and CH3 group is bonded to this position. When it reacts with HI, so you have to follow Markovnikov rule according to MK rule. Identify the negative part of the reagent. So here H is positive and I is negative. So this negative part of the reagent goes to the sp2 hybridized carbon, which is bonded to less number of hydrogen. So here this carbon is bonded to only one hydrogen. Here one hydrogen is there, while here there are two hydrogens are there. So this I will get attached to this carbon. So let's draw the structure of our product. So this is cyclohexane, and now this is already bonded to CH3 group, and here I will get attached to the same carbon here, and hydrogen will get attached to the adjacent position. So this will be the structure of your product. Now come to the fifth question. Here bromoethane is given and it reacts with NaI. So this is Finkelstein reaction where halogen exchange takes place. Means Br will take the position of I and I will take the position of Br. So as a result of it, you will get CH3, CH2, I. This will be the product of this reaction. Now come to the sixth question. Here alkene is given, cyclohexene is given when it reacts with Br in presence of UV light. So what will happen when alkene react with Br2 in presence of UV light? So this is cyclohexene and it react with Br2 in presence of H nu. So when it react, one of the bond will break. So we are going to break this double bond, and as a result of it, valency of both the carbons will become free and bromine will get attached to both the carbons. So here one bromine will get attached to this carbon and another bromine will get attached to the another carbon. So this will be the product of this reaction. In the next lecture, we are going to discuss physical properties of alkyl and aryl halides.